welcome to lecture number 20, and as I told you, we will now see higher order linear differential equation, constant coefficient, and how to solve those equations. So, let the equation be like this: plus a y dy dt plus b y is equal to x t. Once again, x t is the input, it could be any reasonable function, y is the output of the network. Now, first of all, what we will be doing is this one. This left hand side, I can write it like this: d square plus a d plus b into y t is equal to x t, where d is the operator, d dt. I can write like this, and this can be factorized, is not? I can find out the root of this equation, that is characteristic equation. Here will be m square plus a m plus b is equal to 0. Characteristic root decides the natural response. Anyway, I will write it like this. So, suppose the roots of this equation, this characteristic equation or this equation plus b is equal to 0. Suppose I can factorize them after finding out the root and say that it is equal to d minus m 1 into d minus m 2 is equal to 0. I can write it like this. So, this left hand side then can be written as m 1 d minus m 2 into y is equal to x t. Okay. Now, this second order system can be thought of as two single order system. How? Let us see. Let I will write it like this. Let d minus m 2 into y t be some z t. It is a first order differential equation, and y t of course, I do not know yet, but if d minus m 2 operates on y t, it will give rise to some function of time, and that I am telling z t, this one. And then I will say d minus m 1 into z t is equal to x t. Got the point? So, this second order differential equation has now been broken up into two first order equations. One is this and the other is this, these two terms. This is very interesting. Z t I do not know yet, but anyway. So, you see, it is from this equation, it is a first order differential equation. Only in place of y it is z t, it is a first order differential equation. Therefore, we first tackle this differential equation, d minus m 1 into z t is equal to x t. This I will write. So, what will be z t? Z t I find out from this, and then I will substitute it here to get the value of y t. My ultimate goal is to find out y t. So, from this differential equation, and this is a first order differential equation, I know what will be the nature of the solution. Z t, the total solution, will be the characteristic root. Characteristic root is m 1. So, sum a into e to the power m 1 t plus k 1 say constant into forcing function is x plus k 2 x dot plus k 3 x double dot up to infinity. That is what we have learned. It is a first order differential equation and z t must be this. So, z t can be obtained, and if z t is known, then I will come to this equation, which is another first order system. It says that d minus m 2 into y t and right hand side is forcing function, which is this one, this whole thing, that is a bar into e to the power m 1 t plus k 1 x plus k 2 x dot plus k 3 x double dot up to infinity. So, it is also a first order differential equation, where from I will get y 2, and the forcing function looks like this, and it is also a reasonable function. Only thing infinite terms, let it be there, who cares, because I know I can write down the solution for y t in one stroke. What will be the solution of this differential equation? There will be a natural part of the solution, and that part of the solution one will be some b into e to the power m 2 t, because characteristic root is here only m 2 e to the power m 2 t plus what? Plus I will first write z t is this one. So, it will be some say k 1, let me use different color for solution due to forcing function. Say this will be equal to some k 1 double bar z plus, because this is z t. So, k 2 bar z dot plus k 3 double bar z double dot and so on up to infinity. That is what we have learned. This will be the thing. Now, I have to put for z t, this one is z t, is not this whole thing on the right hand side. So, what it will be? It will be then, the solution will be b into e to the power m t 2, that is fine. Now, this one, this whole thing you have to multiply with this k 1. If you differentiate this one first equation, what you will get? This first term z dot will be a into m 1 into e to the power m 1 t. So, you differentiate this equation. So, if you differentiate this whole lot of thing to find out z dot t, z is there, this one z dot t, if you differentiate, what terms you will get? Another e to the power m 1 t you will get. See, e to the power exponential functions are such a nice function. You differentiate, integrate, it will, its nature will not be spoiled. It will still remain e to the power m t. Only thing, its scaling factor gets changed. So, this term will be ultimately, so far as this term is concerned, I will collect all those e to the power m 1 t terms from successive differentiation x dot will be also e to the power m 1 t. So, I can say it is equal to a into e to the power m 1 t. What else? Is not? Similarly, z will give you x, z dot will not give you any x, whatever it is. When you differentiate this z dot, it will give you x dot. So, all x I will put together and that I will treat it as a constant and it will give you x t. Similarly, z dot will give you x dot, another x double dot will come here, another x triple dot, but I will collect all the terms having x dot and whatever constant in the bracket I will get, I will write it at x 2 dot. And this way the basic nature does not change ultimately. Therefore, you see the solution when the forcing function or when the system is a second order system will be exactly same. Okay, these steps I am not going to do. I know what are the terms will be present. So, we broke the second order system in fact into two first order system, this and this. Then I solved for z t. Z t becomes the forcing function of this differential equation from where y t can be obtained, that is after all our goal is, and therefore, I have come back to this equation. Forcing function looks like formidable, but it is really not, because characteristic root of this first order differential equation is m t b into e to the power m t. Now, if you put some time, you see this is this fine, but z dot will give rise to x dot x triple dot. Similarly, z double dot will also give rise to x double dot x triple dot. So, I will now collect all the terms involving x dot and those coefficients are constants, let it be up to infinity. So, basic nature of the solution remains same like this. In these derivations, I have assumed one thing, that is m 1 not equal to m 2. Roots are distinct, This is the solution. Got the point? Therefore, what is the thing? If the roots are distinct, writing down from this differential equation, it is given, and this time two boundary condition must be given. Y 0 will be given, y dy dt will be given 0. So, this is the differential equation. I will only find out characteristic root and straight away come to this line. Those things you do not have to repeat, I mean no point, and the rule is once again same. The solution due to forcing function will be linear combination of x and its higher order derivative, and the natural response will be a into e to the power m 1 t plus b into e to the power m 2 t. In the same way, where m 1 m 2 are the characteristic roots of the equation. If you have understood this, in one stroke you can at least write down the nature of the solution. After you find out these solutions, then look at the x t terms as we have done in the previous case. Those problems you can try. Two boundary conditions are given. So, here also this forcing function will alone satisfy the differential equation. From this forcing function alone, if you put right hand side, it will be x t. So, equate the treat that equation to be an identity, get the values of k 1, k 2, k 3 etcetera, whatever it is, and then write down the total solution, then to the total solution apply the boundary conditions to get A and B. That is the rule, clear. Now, only thing is what happens if these roots are not distinct. Suppose I say let the same differential equation dy dt 2 plus of a dy dt plus by is equal to x t, that is the equation given, but the characteristic equation is it comes out to be, suppose a b values are such that it comes out to be d minus m into d minus m into y is equal to x t. Suppose this, so m 1 when roots are repeating, that is m 1 is equal to m 2 is equal to m, such a situation takes place. Do not worry, we will go by this. Once again I will write this equation as d minus m, and I will let d minus m into y to be some function of z t, I will write. So, this into z t is equal to your x t, is not clear. So, I have broken this up into two equations. So, first I concentrate on this differential equation. Here a single root, no problem. So, I will say the solution of this one will be is equal to some a bar, some constant, you could write a also, e to the power m t, characteristic root is m, plus some k 1 bar x plus k 2, I am going okay now, k 2 bar into x dot plus dot 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 up to infinity, k 3 bar x double dot, is not, I am going up to infinity. So, this is the differential equation, but my target is to solve for y. So, I will come back to this equation now. Second thing I have to solve is d minus m into y t, because y t is my goal, what will be the nature of y t, and that I will write d minus m into y t as your z t, and this z t is nothing but this whole thing like a bar e to the power m t plus k 1 bar x plus k 2 bar x dot plus k 3 bar x double dot up to infinity. That is the thing we have learned. Now, so if you remove this z t in between, this is the thing, na? This is the differential equation, first order differential equation, and it is a first order differential equation with a peculiar forcing function. Okay, peculiar, but nonetheless it can be handled. It has got differentiation, it can, and so on. So, this is the thing. Therefore, what will be y t? This part is most interesting now. Y t, total solution, will be what? It is a first order differential equation. It has a characteristic root m. So, b into m t, that will be this equal to 0, it will be this, plus if you write it like this, k 1 double bar z plus k 2 double bar z dot k 3 z double dot and so on up to infinity. This will be the total solution, is not? But you see in this one, there is a forcing function on the right hand side whose exponential thing is e to the power m t, characteristic root is also e to the power m t. Therefore, solution, natural solution of this one, it should be modified. Why? It should be written as b plus some constant c into t into e to the power m t. Because we have seen earlier on the right hand side, if there is an excitation e to the power m t and characteristic root is also e to the power m t, then the solution will be like this in a first order system. A plus some constant into t. Why some constant has not come here? Because you chose 1. It may be k into e to the power minus a t, is not? Therefore, this is the point to be noted. So, I will say the solution of this differential equation, if the roots are repeating, will be b plus c t into e to the power m t plus this one, but you know this e to the power m t can be clubbed with this e to the power m t and so on. So, it will be finally some b plus c t into e to the power m t plus ultimately it will be like this. Up to infinity. So, if the roots are repeating, then the natural response will be like this. That is, one will be b into e to the power m t plus another will be c t into e to the power m t. Because of the fact on the right hand side you can easily identify the characteristic root is m, excitation is e to the power m t. Therefore, if you go to the basics fundamental e to the power minus m t, if you multiply it will become constant, integrate it will be some constant into t. Got the point? So, similarly, this is the thing. Therefore, there may be two options coming. One is roots are distinct. If roots, if if two roots are repeating, this will be the thing. I will just point out which I am not going to do. Suppose you have a third order differential equation d cube y dt cube plus a d2y dt2 plus b dy dt plus c y is equal to x t. What I will do first? You first find out the, write down the equation in this way, d m1 d minus m2 d minus mt, factorize it into y is equal to x t. So, this you start with z and so on. So, 3 first order system you can make, but whatever you do, I am telling you solution will be, it is so nice a thing to remember, easy to remember. It will be, if roots are distinct, you will simply write, okay, natural solution will be this b into e to the power m2 t plus c into e to the power m3 t, that is the thing, and plus k1 into x plus solution due to forcing function x dot plus k3 x double dot and up to infinity. Linear combination of the forcing function, and so verbally you say to yourself, okay, this will be the linear combination of x and its higher order derivative up to infinity. So, knowing this differential equation, only thing you have to factorize it to know the values of m 1, m 2, m 3, then rest of the things I know. Okay, this is 90% of the work done. Then the second part is how to find out k 1, k 2, k 3, forcing function alone, solution due to forcing function alone satisfies this differential equation, put it there, treat it as an identity, equate the coefficients etcetera of the like terms of the left hand and right hand side, get k 1, k 2, k 3, put those values. Then your step will be to determine A, B, C from the total solution, and what will be 3 boundary conditions will be needed. In fact, 3 will be given, dy dt 0 and d2y dt2 will be also given. These 3 if given, I can generate 3 equations and get the solution. If this is true, if roots are distinct, m 1 not equal to m 2 not equal to m 3. Suppose let us say m 1, m and m 2 and m 3, suppose if m 1 and these 2 roots are repeating, 2 roots repeating. Oh, I can easily write y t. First of all, m 1 is alone. So, it will be total solution will be a into e to the power m 1 t over. These 2 are repeating. So, it will be b t plus c into e to the power m t. Mind you, 3 constants will be there, but t appears for reasons which I have explained in my previous example. Why it will be different, plus k 1 into x plus k 2 into x dot plus k 3 into x double dot plus up to infinity in one stroke. If all the 3 roots are repeating, if m 1 equal to m 2 is equal to m 3 is equal to m say, then I will say total solution will be, you can easily see, it will be a, it will be say a plus b t plus c t square into e to the power m t plus k 1 x plus k 2 x dot up to infinity. Got the point? Therefore, you will be able to handle situations very efficiently. We will later see that solution of differential equations can be avoided by using some transformation, that is using some Laplace transformation. You can also solve for the currents, that is solving differential equations altogether can be translated in some sort of algebraic equation, differential equations by using Laplace transforms. We will devote some time on that also, and that is very good, nothing wrong in that. But people still believe that differential equation is given and you do not take any transformation. Are you in a position to tell about the nature of the solution straight in time domain, living in time domain, no transformation, nothing. Yes, I can do that, and this gives you a better insight into the problem. Laplace transform, okay, you go to some other domain, solve it, sort of mechanical things. But here you see people still use them. This is called classical way. Classical way of solving differential equation. Clear? See, while telling about the roots, I told you that there are repeating roots, there are distinct roots. It may so happen that the roots may become complex number. Nothing doing. Even if roots are complex numbers, what happens? They will appear in conjugate pairs and they are not equal, distinct. Therefore, all rules that we have developed can be easily applied. Even if the roots are complex, I will write M1 some A plus JB like that. But interesting thing is roots, if one root is complex, there must be another root which will be also complex and complex conjugate of this. These are all the advantages. We will discuss and solve problems on that. But essential thing is, to conclude this particular topic, is that, for example, I am telling you that suppose you have a differential equation d2y dt2 second order, let us put some number here plus 4 dy dt. We will be mostly concentrating on second order differential equation, although third order, any higher order system you can do. Suppose this is 6. Any number, good number, and plus y is equal to, suppose some t. Let us not bother. Okay, this is the thing, differential equation given second order, and it is also given that y 0 is 0, all initial conditions relaxed is a term, which means the initial conditions that you need are all set to 0 when you want to solve. You want to get the solution for t greater than equal to 0, and these are the two boundary conditions given. Suppose this is the thing. Then the characteristic equation is m square plus 6 m plus 1 is equal to 0, is not? Or should I put 6? 5 here, 5. Let us put 5 there, so that things come. So, you see this is the characteristic equation. On the right hand side there is a forcing function which depends on t, it is a second order system, but how simple it will become, let us see. This one can be written as m plus 3 into m plus 2, no. So, this is 6, m 3 m 5 plus m 1, let this be 5, sorry. So, this you factorize, you get this, and that is equal to 0. What are the roots? m 1 is equal to minus 5 and m 2 is equal to minus 1. They are distinct, real distinct. Even if it is complex, they are distinct, different. Complex means different, no, nothing doing. So, this is the thing. Then I will say the solution straight away now, no this way that way, straight away y t I will say it will be equal to a into e to the power minus 5 t plus b into e to the power minus t minus 1 plus k 1 into t, this is x t, linear combination of the forcing function plus its higher order derivatives k 2 into differentiate t 1 and no other terms. Here finishes, everything is finished. Then I will say that k 1 t plus k 2 is solution due to forcing function, Therefore, this will satisfy this equation, that is d 2 dt 2. This I will not complete, I will leave it as an exercise k 1 t plus k 2 plus 6 d dt of k 1 t plus k 2. This satisfies the forcing function plus 5 k 1 t plus k 2. This is the term solution due to forcing function, and this must be equal to t. How many constants are there? K 1, K 2. So, you differentiate, there is no t square. So, coefficient of t from this side and that side will be equal, and constant, there is no constant on the right hand side, but if there is constant, that should you equate to 0, get k 1 k 2, then put it here, then put the B C boundary conditions. So, please complete this problem on yourself and generate problem on your own, any problem, okay. But only restriction is you put constant coefficient, do not make the coefficients time varying, etc. And also do not make this function on the right hand side an impulse function, everything will be in place. Thank you.